Okay, it's my great pleasure to introduce our CAP speaker for the week, who is Dr. Gary Melnick from Harvard Smithsonian Center for Astrophysics. Gary started his career at Cornell as an undergrad in physics. After graduating there, he went and spent a year at IBM, where IBM actually had an astrophysics group. They were interested in applications. Sounds actually familiar to like this building. Then he went back to Cornell to work on his PhD in astronomy, and he worked with Martin Harwitt. Grad students take note. There's an amazing book that Martin Harwitt is like a legend, and he has this really cool book from probably 1985, I would guess, called Astrophysical Discoveries, and he lays Cosmic Discoveries. And he basically lays out kind of the history of astronomy and like what things revolutionized astronomy and what it is. And he kind of laid out this concept of like, well, there's new technology and then new data and then people interpreting this and then theory and this virtuous cycle. So Gary worked with Martin, and his PhD thesis, which I've known Gary a long time, and either this escaped me because I've killed his brain cells, or he'd never told me. Gary's thesis was to make a 1-pixel detector that was a spectrometer that he built by hand, and then flew on a Learjet, basically on the edge of space, and made the first ever detection of C+. And at the time, they didn't know exactly what wavelength it was, so he went looking for it and built the instrument that did that. So thank you, Gary. That was important for my career. After he finished his PhD in 1980 and then moved to CFA, where he's been ever since. He first started working on a helium-cooled mirror on the space shuttle, which did important studies, basically concluding in space telescopes need to be not in the space shuttle, but further out in space. He was the PI of a NASA mission called SWAS, which studied the molecular composition of the Milky Way from 1998 to 2005. He was deputy PI of the near-infrared camera on Spitzer called IRAC, which was NASA's infrared flagship mission before JWST. And currently, he's the science lead for biogenic ices for NASA's next big survey mission called SPHEREx, which is supposed to launch next year. And so SPHEREx was kind of originally conceived as like a cosmology probe, but it turned out if you build a near-infrared spectrometer and do an all-sky survey, it has applications in all kinds of interesting like subfields of astrophysics. And Gary is one of the very important leads talking about kind of all the other stuff you get when you try to do a cosmological survey. So Gary's going to talk about all that. So let's welcome Gary to the auditorium.
Well, thank you, Joaquin. It's a real pleasure to be here. I've never been to the University of Illinois before. I haven't seen much of your campus, but I've thoroughly enjoyed the time I've spent with the students that I've met since being here. So I will talk today about a number of things, culminating in a description of this mission that I'll describe toward the end of the talk. And the focus of my talk today will be on that aspect of the mission that bears on understanding how newly forming planetary systems get their basic ingredients for life. So I will start with a brief unofficial history. This is my own delving through Google as much as anything, of the history of Follow the Water, NASA's motivating theme for the search for life beyond Earth. I'll mention the first detection of water in interstellar space. I'll describe how water's formed and the challenges to studying it. I'll discuss the first comprehensive mission to understand water, SWAS, sub-millimeter wave astronomy satellite, and the puzzles that it initially presented us. And then I'll talk about the wisdom we gained from puzzling through the SWAS results that led to our proposing the SPHEREx mission, and I'll describe that in detail and then conclude. So let's start with a brief unofficial history of the follow the water theme. Galileo was the first one to look at the moon through a telescope that he made. That was in 1610, but it was the Dutch astronomer Michael van Langren that published the first map of the moon, and he referred to the dark areas that he saw through his telescope as maria, which is Latin for seas, and put into writing this view that marked the possibility of oceans on the lunar surface. And we might consider that absurd in light of what we know today, but it is noteworthy to remember that the first landing on the moon occurred in the Sea of Tranquility. Moving ahead to the 1800s, Giovanni Schiaparelli mapped Mars with a somewhat more capable telescope at the observatory in Milan, where he was the director, and he saw what he believed were these intriguing linear features that he called canali. Now, in Latin, it can mean naturally occurring features like trenches or canyons, etc., or it could mean manufactured structures. However, 1877 wasn't too long after the Suez Canal was completed in 1869, which was considered a marvel of engineering, and it fueled the speculation that Martians similarly were building canals, and given the number of them in the maps that he made, the suggestion was that they were an advanced civilization. These musings by Schiaparelli inspired Percival Lowell, who was a wealthy Bostonian, who was so motivated by Schiaparelli's writings that he bought an observatory, which still stands today, Lowell Observatory in Flagstaff, Arizona. And over the course of some 23 years, published 3 books, each with a somewhat more ambitious title. First was Mars, Mars and its Canals, and Mars as an Abode for Life. And his thesis was that these were indeed canals designed to channel polar water, he thought, from the poles to the equator as seasonal demand required. And these notions were so gripping to the general population that they made their way into such publications as the Atlantic Monthly and Scientific American. The other aspect of the connection between water and life goes back to a very renowned Harvard biologist, Lawrence Henderson, who wrote a seminal work in 1913 called The Fitness of the Environment, in which he says, and I quote, "Life necessarily must be based on carbon and water and have its higher forms metabolizing free oxygen." Now, sometimes later in the 1970s, Carl Sagan advocated a more expansive view of the possible environments for life, and he sort of famously cautioned, because Lawrence Henderson was made of carbon and water and metabolized free oxygen, he had a vested interest. It was sort of quintessential Carl to frame it that way. But nonetheless, it's what we know as opposed to what we imagine, and it remains a guiding principle of NASA's search for life in the solar system and beyond, to follow the water. And testimony to that belief is the recent launch of the Europa Clipper, which is designed to go to Jupiter's moon to follow up on evidence of a subsurface ocean on Europa. And of course, the next big flagship mission, Habitable Worlds Observatory, one of their main objectives is to study around 24 extrasolar planets using spectroscopy to search for water and other biosignatures like oxygen and methane. So follow the water remains a pretty gripping theme for the search for life outside of Earth. So in the late 1980s, early 1990s, around the time we proposed this sub-millimeter wave astronomy satellite, there were a few facts that were by consensus regarded as true. Water is an essential ingredient for life. None of the Earth's water was formed on Earth. It was delivered here. But the question remained, where did water form and how did it get here? So now I'll move to the first detection of interstellar water, which was in 1969. So up till, actually late 1968, it was published in early 1969. And it was the detection of water at 22 gigahertz toward the Orion Nebula and SAGE B2 in the galactic center. And this was seminal because it moved the discussion from the theoretical to the real. That is, for the first time, we knew that there was water in interstellar space. A couple interesting things about it was the effort was led by Charles Townes. And for those who don't know that name, Charlie Townes was awarded the Nobel Prize for the invention of the maser, which was, of course, the foundation for the laser. So it was not such a stretch for him and his team to say that the radio emissions are extraordinarily intense, which they were, which led to the belief that this was a cosmic maser. So it was quite fortuitous that Charlie was not only a highly capable laboratory experimentalist, the environment in which he invented the maser, or co-invented the maser, but he used that knowledge to correctly interpret the emission that he was seeing at radio wavelengths at 22 gigahertz. The other thing I found fascinating in this 1969 New York Times article was their incredibly prescient interpretation of the data, and I'll read it. They've detected radio emissions from what appear to be one or more rings of dust and gas whirling at great speed around a central object. It is suspected that the central object may be a star in the process of formation and that the ring or rings may be condensing into new planets. This really was before these concepts were really fleshed out, and I thought it was an incredible leap of imagination and extrapolation that turned out to be true. So water was the sixth interstellar molecule to be detected, and it benefited from the advances in radio astronomy that were emerging in the late 60s. The detection that Charlie made of the 22 gigahertz emission was made from the Hat Creek Observatory in California. And as you can see, starting in the late 60s, but blossoming in the 70s and beyond, with the advent of a host of very capable new radio telescopes, there was a growth, I won't say exponential, but a significant growth in the number of different molecules detected in the interstellar medium. And to Joaquin's point about Martin Harwitz's book, Cosmic Discovery, Martin in his book cites a number of examples how the introduction of new assets, new equipment, new telescopes was rapidly followed by new discoveries. The 5-meter telescope at Mount Palomar yielded a whole host of new discoveries in 2 or 3 years after it was commissioned. And this is similarly the byproduct of 4 or 5 major radio telescopes coming online. So now I'd like to move to how water's formed in the interstellar medium and why it's so challenging to study this molecule. So typically chemical reactions occur in the interstellar medium through collisions of different species and the exchange of nuclei in those, the addition of an oxygen nuclei to a hydrogen nuclei. But you need a certain energy for that exchange to happen. And at very low temperatures, that's difficult if you're talking about two neutral species. But if you say that these species are ionized, and in this case, by cosmic rays, it starts the chemistry by ionizing H2, you have Coulomb attraction that will bring species together and allow for this exchange of nuclei. And it was this process that Eric Herbst and Klemperer published in 1973, which I regard as a very seminal paper, that described how you could form molecules in general, but in this case, in particular, water, through a rather short sequence of ion-neutral reactions. This is not fast. It can take 10 to 100,000 years to produce a significant abundance of water through this mechanism, but it is effective. At higher temperatures, you overcome these barriers just through the energetics of the atoms and molecules, but these have barriers to them. These are endothermic reactions that require over 1600 degrees in general to proceed, though they will proceed at 300 and 400 degrees. And this actually is a very effective way of producing water, but because of the high temperatures involved, it usually only kicks in shocked gas regions where the gas is warm or hot. And by volume, by number, such hot gas regions are a very, very small percentage of the general interstellar medium. So if we're interested in the formation of water writ large, I won't be talking about this pathway at all because it doesn't represent a very high percentage of the water formed. So in the 1980s, there were a spate of papers that looked at what cools the interstellar medium. And if you're going to have collapse of gas to form stars, you need to radiate away that energy of the collapse. It's like a piston pushing down on gas. As gravity wants to pull this gas together, it's going to heat that gas. And if you can't shed that energy, eventually the collapse will be resisted and stopped by thermal energy. And the main gas coolants, in these plots I'm showing the cooling power with greater cooling power toward the top of these plots and the gas density at the bottom for three temperatures, 10, 40, and 100 Kelvin. And the key takeaways from this are that for densities greater than about 3 by 10 to the 4, which is typical of dense molecular clouds, it's water and it's CO that dominate the cooling in these clouds, with O2 not being insignificant. We fully expected to detect O2 throughout the interstellar medium. It's useful to consider the energy level diagram of water, which is actually two species, an orthoflavor and a paraflavor. You can switch between one and the other through collisions, but otherwise they're totally separate. And the 22 gigahertz detection I mentioned before has an upper state energy of about 642 Kelvin, which is not optimal for studying cold molecular gas. Instead, you want to focus on the transitions below 200 or even 100 Kelvin. And when you look at those, you see that all of these either ground state or first excited state transitions are all in the far infrared or submillimeter, where the atmosphere is not very cooperative. And it's not cooperative largely due to absorption by water vapor in our own atmosphere. So for example, this is the ground state transition of ortho water at 557 gigahertz. This is the atmospheric transmission, percent atmospheric transmission divided by 100. So 1 is 100% transmissive. And you can see at the center of this line, even at 30 kilometers altitude, this is a balloon altitude of about 100,000 feet, the atmosphere is entirely opaque. There's enough residual water at that altitude to block any emission from outside the atmosphere. And this is the region plus or minus 200 kilometers per second of the line center, which basically means it precludes the observations of almost any or all objects in the Milky Way and nearby galaxies. Likewise, if you look at the other low-lying transitions, they all fall within rather strong atmospheric features, making their study, it's certainly in the Milky Way, impossible even from a balloon. So what do we do? What we did.
Okay. So I have a question about the, I'm blown away by this para north of the water. I was not aware of it. The amount of water that we have on our planet was delivered to us, right?
Yes.
So we have no say in, we are not creating more molecules of water.
That's right.
So do you know, or is it know, what is the fraction of para versus ortho that we have on the planet, or does it have any implications for life and so on?
The ratio on Earth is 3 to 1, ortho to para. And that is the equilibrium state of water at 300 Kelvin, even in interstellar space, and we've measured it. We've measured both ortho and para water. In very cold regions, you can get almost 100% para. And people have tried to use the ortho to para ratio as a chronometer, as a timepiece, because you can calculate how much time at a given temperature it takes to convert all para water into ortho water. And if you measure that ortho to para ratio, and you know the temperature of the cloud from your observation of other molecules, you can determine the age of that cloud with a fair bit of accuracy. Now, it's only been done to a few lines of sight, but maybe that's more information that you were seeking. So we realized that we had to do better than balloons. We had to get totally beyond the Earth's atmosphere if we had any hope of studying water in its dominant environment, which are these cold molecular clouds. And that was the motivation for the proposal that I led with a team, a great team of collaborators for the submillimeter wave astronomy satellite. It was the first Explorer mission in NASA's sequence of Explorer missions. By the way, SPHEREx is an Explorer mission as well. And the goal of SWAS, this acronym, the goal of this mission was fundamentally to study these 4 basic lines: the ground state transition of water, which, as I showed you, cannot be done even from a high-flying balloon, a low-lying transition of O2, atomic carbon, and 13CO. In this talk, I'll focus on what we learned from the study of water in O2, but I just want to remind us that the upper-level energy of these transitions is very well tuned to the temperature of these molecular clouds. So we had every expectation that the emission we would see in these 2 species would be quite strong. In the course of the mission, which went from 1998 through 2005, we looked at about 7,500 lines of sight in the galaxy, but there was a puzzle. We detected water toward almost every line of sight we looked at. We saw the ground state water transition everywhere. However, the range of intensities was nowhere close to what we had expected. And I mentioned that we observed about 7,500 lines of sight, but it wasn't toward a restricted region that might be biased, it was over 300 different galactic star-forming regions.
What was the expectation before the launch?
The expectation was that we would see water. I mean, you saw in these cooling curves I showed that water would be everywhere, and that O2 would be everywhere, that they would permeate the cloud, and we would see them everywhere we looked. And in fact, O2 was thought to be, it was unknown. No, there were zero attempts to observe O2. So we built SWAS with an extraordinarily large chopping angle, 3 degrees, in order to make sure that we got off of the CO emission, which we took to be the gold standard for measuring, the extent of a cloud. And we determined by looking at hundreds of maps that 3 degrees in any direction would get us to a place where there was no molecular emission. So I'll get to what we found with O2 in a minute. It's an important part of the story. But it turns out, if you look at the radiative transfer of water, that for densities below a few by 10 to the 7, the water energy levels are subthermally populated, which means that it's effectively optically thin. The lines can have a large optical depth, but the way that I like to think about it is like a frosted light bulb, that the light might bounce around, scatter a lot, but all the photons end up getting out. So it's what they call effectively thin, which would mean that the flux that we expected to measure would just be the product of the H2 density, the main collision partner, and the column density of water. Since we could readily measure the column density of CO, this just simply becomes the column density of CO times the abundance ratio of water to CO. And you can show that it's directly related to the antenna temperature, the peak antenna temperature you measure times the velocity width of the line. So based on the range of H2 densities that have been measured, and certainly the 12 CO and 13 CO column density measures, we expected to see a range of water, of peak antenna temperatures over a range of 10 to 100. This was a histogram we made about midway through the mission, showing on the y-axis the number of sources, and on the x-axis the peak antenna temperature in the water line. And what we found is that almost 80% of the sources we looked at had a peak antenna temperature within a factor of 2 of about 170 millikelvin, which puzzled us. We really didn't understand why it was such a narrow range. So we conceived of an experiment using SWAS, and then I repeated it with Herschel as a way to try to flesh this out. And to do it, we used the Orion Nebula as our test bed. There is a ridge of material, I'll show you in a minute, that's quite extended, and it's face-on geometry to us. So every beam, in this case I'll show you Herschel beam or SWAS beam, that we applied looking toward this ridge was sort of an independent measure of the species we were looking at. And I'll get to that in a minute. The ridge is so extended that it allowed over 2,000 Herschel Hi-Fi map positions to be put on the ridge. And because Orion is such a strong nearby source, the signal-to-noise ratio that we got on the various spectra we took were rather high, and the ridge itself is warm internally, which means we didn't have to worry about CO freezing out on dust grains in the ridge, and we were using CO in ratio to water, as I mentioned earlier, as part of this test. So this is the test in its cartoon form. So we were looking at 2,000 lines of sight through this ridge. And if water permeates the gas, we expect that the column density of water we derive to be proportional to that of 13CO or C18O. However, if the water is restricted in this distribution for whatever reason, we didn't expect that relationship to hold. So using what was then in operation, the 5 College Radio Observatory, we mapped the ridge in 13CO and C18O, and we did C18O out of concern that there may be some lines of sight here in which the 13CO might be optically thick, the C18O being optically thin throughout. And this was the Herschel map that we got of water, the ground state 557 gigahertz transition of water from those 2,000 positions. We regridded the data. This was the original Herschel grid. The size of the 557 beam on Herschel Hi-Fi is shown here. The beam on FCRAO, which was at much lower frequency, allowed for only 834 positions. So we regridded spatially the Herschel data to match that of 5 College Radio Observatory. And we proceeded to reduce the data. So we took these 834 positions, and each line of sight represented a different column density and a different extinction into the cloud, and we binned them to improve the signal to noise. And we got this for the ratio of 13CO to C18O as a test of whether we were on the right track. Now, given the isotopic ratio of 16 to 18O and what had been measured toward Orion through a number of different molecular species of the ratio of 12C to 13C, we expected that the 13CO to C18O would equilibrate somewhere between a ratio of 8 and 12. And in fact, that's what we see here. And the reason that there's this rise here is not an excitation effect. It's due to the fact that the column density of C18O is lower than that of 13CO. So its self-shielding lags behind that of the 13CO, and it's only deep into the cloud that you have fully shielded 13 and C18O. So what did it tell us about the water? This is the ratio of the water to the C18O, and what we found there was that the water, in fact, peaks within about 10 magnitudes of extinction of the cloud surface, and then drops off rather precipitously deeper into the cloud. Supporting evidence for this was obtained. This is a SWAS strip scan. We did other strip scans, but it tells the story. This is an edge-on cloud now, not face-on. And we looked at a position outside the cloud, at the cloud surface, and deeper into the cloud. And you can see as well that there's evidence that the water emission is strongest at the surface. And I can describe it later if you wish, but we worried initially that this might be an excitation effect, but it is not. And I can, if you're curious, I can discuss it at the end of the talk. Now, what about the O2? It turns out it was a pretty crucial piece of the puzzle. In the 7,500 or more lines of sight that we examined with SWAS, we only got a 2 sigma detection of O2 toward maybe one line of sight. Essentially, it was totally absent. And as the PI of this mission, I was getting worried that maybe the O2 receiver wasn't working. I mean, I didn't want to claim that nature does not produce molecular oxygen, only to find out later that the receiver wasn't working. And what worried us was this, you don't have to worry about the details here. This is the ion-neutral reactions that lead to the formation of O2. But each of these reaction rates have been measured in the lab and are well known. There was nothing in this chemical scheme that would suggest that O2 would not be produced. So this was a puzzle, and as I say, I worried that it might have been an instrumental effect. So I could not complete the mission without knowing if that receiver was working. But to determine whether it was working, I had to look at a source that I knew had molecular oxygen. And the only source that I knew had molecular oxygen was the Earth. And we were not allowed to look at the Earth because of thermal effects and linearity concerns. But I wasn't going to end the mission with that uncertainty. So we labeled the Earth as an exotic-sounding target name. And we, on a weekend, we overrode the 2 layers of bright object protection that was afforded us, much against, I did it on a weekend so that it was somewhat out of view. But we looked at a tangent line in the Earth's atmosphere for a few seconds, and we saw this detection of O2 and 2 ozone lines here. This is about 3 or 4 seconds of data at a tangent line at an altitude of 73 kilometers, which was a huge relief. I mean, it told me, yes, the receiver was working. I was relieved about that, but now I pivoted back to worrying what was nature telling us.
How many years into the mission was that?
This was about, let's see, this was 2000. This was about a year, yeah, almost 2 years, a little bit less than 2 years into a 6-year mission. But, you know, I didn't want to go 6 years with a dead receiver, but we knew that it was working as intended. So now we pivot back to the puzzle. Where the hell is the O2? We looked at this scheme again, and we said, if somehow the O2 is, the oxygen is unavailable in this scheme, you can suppress the subsequent reactions and therefore the abundance of O2. Well, how do you suppress the oxygen, the atomic oxygen? And you do it in this fashion. This is the third way that you form water. You have oxygen that strikes a dust grain, and these dust grains, let's bear in mind that hydrogen is 10,000 times more abundant than oxygen in the interstellar medium. So these dust grains are crawling with hydrogen atoms, and every once in a while an oxygen atom hits the grain, and it's the very light and mobile hydrogen atoms that find their way to the oxygen atom and hydrogenate it, first forming OH and then water. And water is a polar molecule, and at the temperature of these grains is very sticky to the grain. It takes heating these grains to above 100 Kelvin before they sublimate from the grain surface. So we hypothesized that the solution to all of these problems is that if oxygen is locked in water ice, you can greatly suppress the O2 abundance. Now, there are ways of getting water off the grain that are important in molecular clouds. You can, near the cloud surface, far UV photons can apply enough energy to kick the molecule off the grain. You can get sputtering, just a hard enough collision of molecular hydrogen can kick water off the grain. Or, as I said before, just heating the grain, as in the inner part of, let's say, a protoplanetary disk, can heat the surface of the grain enough to cause the water to sublimate. So the picture that emerged from the SWAS mission is the following. Here I plot the abundance of gas phase water and depth into the cloud. And in the first couple AV, the water abundance is quite low because any water that forms in the gas phase or even on grains will get photodesorbed and then photodestroyed. Deeper into the cloud, between an AV of, let's say, 3 and 8, the far UV photons are attenuated enough that photodesorption and photodestruction decrease in their effectiveness, and you effectively get a peak in the water abundance, slightly above an abundance relative to H2 of 10 to the minus 7. And then deeper into the cloud, essentially the far UV photons are gone, and any water that either forms on the grain or water that formed in the gas and then strike the grain stick to the grain, and the gas phase water abundance drops. And this is how we think you end up with this very narrow region of gas phase water that is consistent with the absence of O2. So we did some modeling, Dave Hollenbach and myself and Ted Bergen and Michael Kaufman did modeling of both the gas phase and the ice abundance in molecular clouds as a function of the far UV field and the gas density. The solid lines here are the gas phase water. The dashed lines are the ice. In this case, as you rheostat up the far UV field, this transition layer, this surface layer of gas phase water moves in because you're destroying more at the surface. Similarly, in an opposite direction, as you rheostat up the gas density, the densest gas will shield from UV photons most effectively, and you get this zone of gas phase water closer to the surface. But the key feature here is that in all cases, the ice, the amount of water contained in ice is about a factor of 1,000 times greater, so we predict, than that in the gas phase. And this needs testing. And if true, it means that more than 99% of interstellar water is locked in water ice, and follow the water really means follow the ice. So it was this as a backdrop that motivated us to propose SPHEREx. And I would correct one thing that you said at my intro. Actually, the water study preceded the cosmology in the formulation of this mission. And then, you know, we thought, what can we do when we're off the Milky Way? And cosmology was the obvious thing to do. So we proposed SPHEREx, and it was selected in 2019. We're scheduled to launch in February of 2025, a few months from now. It is an all-sky infrared spectral survey. I'll explain the details. Wavelength coverage between 0.75 and 5. Spatial resolution of 6.2 by 6.2 arc seconds. The baseline mission is 2 years. We do a complete 4-pi steradian of the sky, every position with a spectrum. That's 13.8 billion spectra per survey. And we do it every 6 months, so we will do 4 independent all-sky surveys. And we will survey everything brighter than an AB magnitude of 18. If you think in terms of magnitudes, which I don't, but a lot of people do, 5 sigma. The 3 main science themes driving the mission design are cosmology, as I mentioned, with Olivier Doré and Jamie Bach leading that effort. Survey of the ice content of the Milky Way, which I'm leading, and a measure of the history and light production to constrain galaxy formation in the epoch of reionization. That's being led by Asantha Correa at UC Irvine. This is SPHEREx at a glance. This is a cutaway of SPHEREx. It is a 20-centimeter telescope with a total field of view of about 3.5 by 11.3 degrees. It is passively cooled. the telescope to 80 degrees and the detectors to 55 degrees. Our spectrometers weigh 25 grams. They're linear variable filters, and I'll describe that in a minute. And the spacecraft bus is provided by what was Ball Aerospace Corporation, but is now BAE Systems. This is a picture of the telescope assembly. These are thermal radiators that look out at the black of space. There is on the side here, it's sort of hard to see, but an anti-sun radiator that with a copper strap that cools the detectors, and then our star trackers. And if we peel away that outside, what you see is a very simple optical scheme. It's basically 3 mirrors shown here, and a dichroic that splits the light shortward of about 2.5 microns and longward of 2.5 microns to 3 detectors each. So in total, we're flying 6 Hawaii 2RG detector arrays, and if you're not familiar with that jargon, these are the same detectors as used in the short wavelength instruments on JWST. And these linear variable filters are these little pieces of glass that sit right on top of the detectors. Let's see. The way that we build up a spectrum is by moving the telescope. And so we move across the linear variable filters and we build up the spectrum. Each position on the variable filter is a different wavelength. And so it's a little bit different than getting a spectrum in one shot, as if you were working with a grading instrument, for example. A complete spectrum is 51 exposures. We have 102 colors across 0.75 to 5 microns. Let's see. This is a picture at Ball in September of SPHEREx. These 3 large funnel-looking constructs are not part of the thermal system. They block the light from the Earth. So they're what we call photon shields. And you can see the star trackers here. If the lighting were a little better, you could see the cover on the telescope there. And this is how we take the data. We are in a sun-synchronous orbit, meaning that we orbit perpetually at the terminator between light and dark on the Earth for thermal reasons with the spacecraft. And we build up spectra by moving in small jogs to fill out the spectrum I showed you in the fashion before, and then we make a large jog to a new field, and we step. And as the Earth goes around the sun, we just keep doing what we do in this terminator between light and dark on the Earth, and we allow the Earth motion around the sun to fill out the whole survey area. This insert here is intended to show coverage of the full sky. And in 6 months, we get it all. So in each orbit, we attack all 3 of our major science themes. As we scan through the Milky Way, we do the ice survey. When we're off of the galactic plane, we do cosmology and inflation. And because we cover the caps of the orbit, on every orbit, we go especially deep here and here, and that's where we do the very faint extended background light for our reionization and galaxy formation studies. I'll mention that the spectrophotometry data will be made available to the community about a year after launch. After the completion of the baseline mission, which again is 2 years, we have a year to process and reprocess all the data, at which point all of the data will be freely available to the community. So returning to the ICES theme, so we will study the ICES through absorption spectroscopy, such as shown here, and we will do so through a large diversity of clouds with the intention that by sampling clouds at every stage of their evolution, we can follow similarly the evolution of ICES from diffuse clouds through dense clouds, through YSOs, and hopefully protoplanetary disks. SPHEREx has 6 bands. These are the wavelength limits of each band. Below here is the resolving power of each band. Of primary interest to us are bands 4, 5, and 6, because that's where the gold is for us. And what do I mean by that? This is a table from a very nice article by Erica Gibb, showing all the different ice features between 2.9 and 4.9 microns. And of particular note is the presence of strong water, methanol, CO2, CO, and OCS, which is a major carrier of sulfur, which is an important element for life. This is an example of a spectrum obtained by the Infrared Space Observatory, an ESA-led mission in the 1990s toward the galactic star-forming region W33A, and you can see that these ice absorption features are recognizable and in many cases quite strong. So if you're wondering if the lower spectral resolving power of SPHEREx poses a problem, it doesn't, because these are solid state features, so they're not inherently narrow. So here I plot the ISO spectra taken with a resolving power of 700, greater than 700, and I overlay what we would see with SPHEREx in band 4 with a resolving power of 35, band 5 110, and band 6 with 130. And you can see that we do a pretty good job of reproducing what's seen at higher spectral resolving power. Now, one of the challenges to studying ICES is that there is a long list of factors that could affect the composition and abundance of ICES. And so you need a large sample to do a statistically significant sample and tease out these differences. I mean, here I list just some of the effects that could ripple into the composition and abundance of ICES. Unfortunately, the sum of the number of ice spectra produced by the Infrared Space Observatory, ISO mission, Spitzer, a Japanese mission called Akari, and even JWST to date have only produced about 250 such spectra, which is woefully short of what is needed to do a statistically significant study of all of these potential influences. So to map the galaxy in ice absorption, you need a large number of background candles to do this absorption, but nature provides such a large number. If we look at the Planck map of the plane of the galaxy, they did the full sky, in 12 CO ground state transition, between plus and minus 5 degrees of the galactic plane, there are over 30 million WISE point sources available, whose positions and fluxes have been very well determined. So what we did is we went through these 30 million potential background candles, and we applied 3 top-level criteria. One is that there's evidence based on the WISE colors plus 2 mass for intervening gas and dust. We don't want to look along a line of sight where there's no evidence of any absorption. 2, we threw out those point sources that were closer to each other than 6.2 arc seconds, which is the size of our pixel, because you could run into a situation where one of the sources is indeed behind the cloud producing absorption, but one might be in front of the cloud, which fills in the flux in those absorption features, which will just yield a confusing result. So we ruled out through spatial proximity any sources within 6.2 arc seconds of each other. And we set as a goal that the signal to noise in any resolution element, any delta lambda, be 50 or greater in the water band, our band 4. And so what is the end product of that? It's this. We come up with more than 9.9 million targets. This shows our best estimate of the visual extinction along each of these lines of sight. This is a little bit hard to digest, so let me break it down into a smaller region. This is a 9 degree by 7 degree region of Cygnus. This is a map, a mosaic made from WISE data. And if your eyesight is good, you see this little yellow rectangle here. That is the size of our JWST early release science observation toward the chameleon cloud. So it's not in this cloud, but this is the size of the region we studied with JWST. And this is what we'll do in this region with SPHEREx. We have over 150,000 targets within this region. This is a breakdown of the extinctions, the number of clouds we estimate with the extinction on the x-axis. And the key thing here is that we sample in a statistically significant way a very broad range of visual extinctions and therefore cloud depths with more than 80,000 lines of sight toward regions with an A sub V greater than 30. I mentioned signal to noise. 98% of our selected targets have a signal to noise of greater than 50 in each spectral element, which is more than 9.7 million targets for the water and complex organic molecules. In band 6, our sensitivity isn't quite as high. 36% of our targets have a signal to noise greater than 50. But if you consider signal to noise greater than 20, that's more than 88% of our targets, which is still pretty good. One of the goals that we set for ourselves with JWST that has been quite frustrating and affected our approach to the analysis of the SPHEREx data was determining what is the composition of the ices. These ices we now know are not pure. When you talk about CO2 or CO or water, it's not pure water. It's a mixture. And this is one example. This is a 13CO feature that was measured with NearSpec for 2 different objects shown here. And you see that the combination of laboratory spectra that were needed to produce a good fit to this JWST measured spectrum. This is a challenge because it's based on available lab spectra, which may not include all the relevant species or mixing ratios or temperatures. And as you can see, there's a degeneracy. You get virtually equally good fits to the JWST data if you assume warm or cold ices. In addition, at least JWST has access to ice features longward of 5 microns that can somehow perhaps distinguish between these 2 possibilities. On SPHEREx, we don't. So due to the uncertainty, and I should add that producing this took months. And if you have 9 million sources, there's no hope of doing it unless we partner with some supercomputer center. I don't know where we'd find such a place. But due to these and the high computational effort, we take a different approach. And that is, what we will do is, after we normalize the spectra, that is, take out the shape of the continuum, we will break these spectra up into a handful of wavelength spaces, and we will convert these to optical depth spectra, essentially, what we call tau space. And to demystify it, the optical depth is just the natural logarithm of the normalized flux here. And the reason we do that is that the integrated optical depth, integrating the tau over this wavelength range, or in this case, wave number range, is directly proportional to the column density of that ice. And the idea, and I just wanted to insert this, that in addition to the features longward of about 2.5 microns, there are weak features at around 2 microns, and there is a noteworthy feature within the 3-micron water feature. It's called a Fresnel peak, and it is produced when the ice has been processed through higher temperatures. So it can give you an idea of whether you see this, for example, in comets that have made frequent passages close to the sun. The ices on the surface are processed, and you begin to see this feature. At any rate, returning to the statistical nature of what we want to do, these are totally simulated data points, but if over hundreds of sources, in this case, let's say, the integrated optical depth scales with the visual extinction, then the story nature is telling us is simple. That is, the ice content in the interstellar medium is just dependent on the size of the cloud. The more cloud there is, the more ice you're going to get. However, if there's a weak correlation, then that means that the ice content isn't simply dependent on the depth of the cloud, but there are other influences, for example, far UV field, cosmic ray rate, cloud temperature, the composition of the cloud, that may have an influence. And the only way you're going to tease this out is through a large sample. We can also do correlation studies by object. This plot is from a very nice paper by Adwin Bugart and collaborators in the Annual Review of Astronomy and Astrophysics in 2015, in which they looked at these 4 ice species and how they grew with depth into these clouds. And what you learn from this is where these fitted curves intersect the x-axis is where these ices start to form. So whereas water ice starts to form at an AV of about 2 magnitudes, methanol only seems to form when you're out near 16 or 18 magnitudes of extinction. And we can do such study with the large number of SPHEREx spectra toward umpteen molecular clouds in the galaxy. So in wrapping up, what role does SPHEREx play in the era of JWST? JWST is without question an incredible machine. It has higher spectral resolving power than SPHEREx, greater wavelength coverage, and greater sensitivity. And it's already yielding incredible information along the limited lines of sight that it has observed, but it is limited. It is not a survey instrument. It does not slew quickly and settle quickly. So the number of sources it can observe over its lifetime will be limited, but SPHEREx will generate a significant number of interesting targets in addition to our own inherent studies for follow-up with JWST. So let me just close with these conclusions. So the takeaways, I think, are that we've discovered over the past 20-some years that gas phase water is ubiquitous in the interstellar medium. Anywhere you have a molecular cloud, you have a surface of a cloud, and in that surface, you will almost certainly form gas phase water, but it exists mainly within these surface regions. And we believe that within such clouds there's a significant reservoir of water ice. If this is confirmed, which we hope to do with SPHEREx, as I said earlier, the mantra will have to change to follow the water and other ice. By obtaining these millions of sightlines with SPHEREx, we hope to be able to break apart and discern all of these factors that affect the formation, distribution, and evolution of ices in general that's not possible to do with a few dozen or even a few thousand sightlines. And finally, working in tandem, SPHEREx and JWST fortuitously will be operating at the same time. We have the potential to really revolutionize our understanding of ices and the role they play in delivering biologically important molecules to planet-forming disks. So I will stop there with one addendum, and that was your request. Joaquin mentioned that earlier in my career, one of the things I did was far-infrared spectroscopy. And I did my PhD thesis using this NASA aircraft with a 12-inch, 30-centimeter telescope mounted in its side. It floated on an air bearing, which means that in flight, the telescope itself was touching nothing. It was the air rushing out of the cabin, which was taken in by the motion of the plane and rushing out this hole in the side of it that caused it to float, and a gyroscope would lock the telescope in place. This is me in 1979, and the equipment that we used. We would look through an eyepiece to acquire the object. I went up with a star chart, and I knew that near Orion or near M17 or wherever, you expected these magnitude 6 bright stars to be, and I would look around until I saw them and then hit a switch, which would then hold the position of the telescope here, rock solid on that position, and a grading spectrometer I designed and built was at the focus of this telescope, and this is a single pixel that I cut myself from gallium-doped tribanium and soldered the leads onto, and we used this equipment to detect the C+ line for the first time in 1980. And yes, aging sucks. I will say that. For 50 years ago.
Questions for Gary? And if anybody, we're over, so if anybody needs to go.
Thank you for the awesome talk. I have a question about this. So this picture you show about water in ice versus gas. We find water at high redshift. Here at Illinois, we found it at redshift 7 in our group with Joaquin. One thing that I have also read in the literature is you find, or in quasars, around the supermassive black hole, huge reservoirs of water. So thinking about all of these things together, you showed like that ubiquity of water in molecular clouds. But I guess what I'm wondering is, where does water fundamentally come from? And if it's trapped in ice versus molecular clouds, does the movement of water on like a galactic timescale occur through the movement of dust grains, or does it occur from the the evolution of molecular clouds? I hope that makes sense.
Well, there's a couple different answers to, I think, different parts of your question. Let me deal with the last part first. What I didn't have time to get into is arguably maybe some of the most exciting parts or consequences of this picture, which is if these molecular clouds harbor a huge reservoir of water ice, then it stands to reason that the dust grains and the ice on their surface will participate with the gas in the collapse to form a protoplanetary disk. And so that is, I believe, the delivery mechanism of water to protoplanetary disk. It's via these dust grains. There's an added benefit, I believe, and that is that water on the surface of dust grains makes them stickier. We've all seen how ice cubes can sort of coagulate into a single blob of ice in our freezers. And I believe that actually the ice-covered dust grains help to build up larger pebbles in the protoplanetary disk midplane. And so I think that's a consequence that we hope to test with SPHEREx. As to the high redshift world, I won't say it's a puzzle. I will say it's very interesting what you're saying. I've been aware, I have not followed in detail, but I've been aware of these various measurements of gas phase water in high redshift objects. And basically, I think what's being seen here is the PDR regions of these photon-dominated regions, these surfaces, heated surfaces of all these molecular clouds and these objects. And I think, put simply, we're finding that water, gas phase water, is essentially a PDR tracer. And it's not unlike C+ in that sense. So if you're seeing C+ and water toward these regions, at least part of that are coming from a common source, which is the surface of these clouds. Now, what I would find interesting is if you see water close enough to the center of these high luminosity sources that it becomes a puzzle as to how it can survive photodissociation. That would be interesting. I just am sort of ignorant of that literature, but that would be an interesting find.
Yeah, can you say a few words about time domain science with SPHEREx?
Yes, I can say in very few words about it, and that is we probably won't have much of an impact. And that is because our survey strategy is baked in. We are, in this respect, we're a 1 or a 0. We're either not functioning, or if we're functioning, we're just going around taking spectra. If a supernova goes off over here, we cannot pivot and observe it. And not just because it breaks up the cadence of the survey, but our whole observatory is exquisitely designed to be passively cooled for the exact geometry of our orbit relative to the sun and the dark side of the Earth. And were we to pivot away from that, we would lose that thermal balance. Now, what we can do is we can compare the same positions in the sky 6 months apart and 6 months apart and 6 months apart. So I would say that for observations requiring very timely and quick pivots to observe, things that I suspect Rubin will begin to surface in great numbers, we probably won't be of much help except by accident. But if there are phenomena that can benefit from relatively high signal-to-noise measurements 6 months apart, then we can help.
You actually started earlier to this, so if you have a bunch of ice-coated grains, that does make them more sticky, you are forming larger structures more quickly, but that has to have some impact then on the statistics for protoplanetary disks, how many of them there are, how quickly they live, how long they survive, etc. So has anybody been able to take a disk made of grains not coated with ice versus a disk made of grains coated with ice and sort of simulate how long they might survive, etc.?
Yeah, I'm not aware of that, but that doesn't mean that people haven't looked at that. I would have the position of I can justify a model that posits grains with ice on them. And of course, when SPHEREx flies, we'll settle that question, definitively, I hope. I would say to the people who posit no ice on grains, how does that happen? Depletion, you can calculate how often water and CO and other molecules strike grains. And at the low temperature of these grains, a number of them, in particular water, are going to stick there because they have such a high sublimation temperature. So I would be hard-pressed to believe models that posited no ice on them. But people may have done it just as the academic exercise of seeing how effective ice grains can be in this respect. And I'll add that one of the mysteries in building up larger elements of the midplane of the protoplanetary disk is how you get from micron-sized grains to millimeter and centimeter size, and it may be in that domain that the ice is of particular help. And beyond that, it's other factors.
Thank you for the great talk. Following up on Charles's question, is there anything stopping you from going for 10, 20 years since it's passively cooled and you can do time domain over 20 years, every 6 months?
No. The way that NASA conducts these missions is that you are selected based on your proposal, which contains a baseline mission. We have stated, we've committed to achieving these 3 major science goals in a 2-year time frame. And that's what NASA has approved. But there are no expendables on board. So assuming nothing fails electronically, and we're working fine, we can keep going. We're at a high enough orbit, about 700 kilometers, that's not an issue. And so it just comes down to what we believe we can tell NASA we could do in an extended mission. And as we discussed at our 10 o'clock get-together with some of the grad students, as you can imagine, there are 100 other projects that you can do with spectra at every position in the sky. And so what may end up happening is that some of these secondary projects will rise to the surface and prove themselves so interesting that with additional data, they could make significant advances. And that could be the basis of a mission extension. Historically, NASA has if missions are working, in the overwhelming number of cases, they extend the mission.
Yeah, thanks for the really nice talk and very interesting survey. I noticed on your plot of the map of the background sources, you have the Magellanic Clouds, but there's very few high AV sources. I'm wondering, are there enough where you could use the Magellanic Clouds for some supplement to like a metallicity gradient experiment that you're doing?
Yeah, that's an interesting question. On a plot like I showed there, not many, maybe only 10 or 20,000 of the high V. So yes, I should have mentioned that in addition to the Milky Way, we have specifically targeted the large and the small Magellanic Clouds, in fact, for exactly the reason that you state in your question, and that is to see the effect of metallicity on the ice content.
I have one departing question. I noticed in your CD, I only found out during your talk, that you overlapped for a long time with Carl Sagan and Cornell. Do you have any personal memories?
Oh, I was asked about that. Carl was a very friendly guy. I mean, I'm not going to stand here and say we were close personal friends. I was a graduate student, but he was very warm and very approachable and would often have lunch with the graduate students. Yeah, I always felt that Carl was a bit unfairly treated in the following respect. In the 70s, he was the face of astronomy to your average television watcher. You know, in the 70s, you had 3 television networks, and he was a frequent guest on The Tonight Show, which was the most popular late-night show. And I thought he was an incredibly effective communicator of astronomy. Sometimes I thought colleagues sort of resented that. I thought then, and I still feel now, that our field has so few really effective and charismatic voices. Some will say Neil deGrasse Tyson is one of them, but you know, we're not talking about a dozen people. We're talking about a few people that we should cherish and hug the ankles of those people that can string together sentences in a way that the average person finds fascinating. And he could do that. At the time, he was working on his Cosmos series, so he was away a fair bit. But he was very approachable, amenable to conversations with graduate students. Unfortunately, and I have no basis for this, but one of the things he was doing as a lab experiment were these Miller-Urey experiments. For those who don't know, you fill up a big glass container with what you imagine to be the primordial gases in our atmosphere, methane, CO, CO2, and you send electrical charges through them like lightning would to see what rains out of that mixture. You know, is it more complex and interesting molecules, or just dissociating those molecules that are affected by these electrical charges? And what they were finding, as the original experiment did, is you sometimes got very complex organic molecules, which is quite interesting as a possible scenario for the formation of prebiotic life on Earth. And so Carl's lab on the 3rd floor of our building was doing these experiments. And I mention it only because there were days we would come in and the place reeked. I mean, we didn't know what, you know, he was creating up there. And the sad fact is that he and a number of the people who worked around there died of cancer. And I have no basis to say it's in any way connected with that. But our space science building at Cornell, which is still standing there, was one of the last buildings built before the energy crisis of 1973 and was not well ventilated. And so I always felt a little bit sad that in the pursuit of what he found so fascinating, you know, he may have caused in some fashion, you know, his own demise. And I also think that his passing, I think it was in 1995, was just a few years too soon to see the explosion of the discovery of exoplanets, which he would have found to be an I told you so kind of thing, but also more than that. I mean, he would not have lorded it over people, but I think he would have just been so exhilarated that what he was imagining would be the logical order of things was actually turning out to be the case. So really nice guy, very approachable. I saw him years later. I left in 1980 to go to Harvard, and I was back at Cornell some 10, 12 years later, and I just rounded a corner, and he was coming the other way, and in an instant he said, "Hi, Gary, how are you doing? You know, how is life, you know, here?" And he was just that kind of person, and I miss him terribly, even though, you know, I wasn't close to him. Some of his you know, faculty colleagues and other collaborators were, but a very nice guy, and he would just be thrilled to see the state of the field now.